We are going to present a novel method of integrating human gaze into attention for egocentric activity recognition. There are two main motivations of this research. Recently, it has been shown that attention mechanisms can improve the performance of neural networks by learning to focus on salient parts of input signals. Also, it has been well discussed in cognitive science that human gaze is closely related to a person's visual attention. Unlike most other previous methods that allow neural networks to learn what and where to focus on from their own responses, our proposed method produces a gaze-guided visual attention to improve the performance of egocentric activity recognition. However, there are some difficulties in using the gaze fixation data. First, there are always measurement errors in the process of recording gaze fixation points due to blinking or rapid eye movements. Second, it is unclear when and how much the gaze data is correlated with visual attention. Third, gaze data is not always available in many real-world situations. To address such difficulties, we introduce an effective probabilistic modeling method. Let's consider a recognition task of predicting activity labels Y given an input clip of egocentric videos X. When we have a discrete latent variable Z that represents the gaze fixation points, we can apply the law of total probability to get the right term. Since this integration is intractable, we can upper bound the negative log likelihood as follows. The benefits of this probabilistic modeling are number 1, it can model the uncertainties of gaze points, and number 2, gaze data is only needed in the training process. When testing the method, gaze data is no longer needed because gaze fixations are predicted by using the learned gaze distribution. In order to compute the expected log likelihood of the loss function, we need to sample the gaze points from Q of Z given X. Gumbel-Max trick provides an efficient way of drawing samples from a discrete latent space. However, the problem is that the argmax operation is non-differentiable, so we cannot evaluate the gradient of the expected log likelihood with respect to phi using a standard backpropagation algorithm. Here, we propose to apply direct optimization method to compute the gradient of the expectation term. It was originally proposed for a discrete variational autoencoder, and it introduced an unbiased gradient estimator for the expectation term with respect to the encoder parameters phi in the following form. We are going to show that the direct optimization method can be applied to our problem if we reformulate the objective function. Since our task is activity recognition, we can model Y given X and Z as a categorical variable. This allows us to rewrite log of P of Y given X and Z as a sum of class-wise log probabilities each multiplied by an indicator function. Now, the expected log likelihood can be reformulated using the class-wise log probabilities as follows. It is decomposed into a sum of multiple expectation terms of the class-wise log probabilities, each multiplied by an indicator function. Since the gradient is a linear operator, we can estimate the gradient of the expected log likelihood as follows. Finally, we can successfully apply the direct optimization method to each class-wise gradient estimator. For the implementation, we use the two-stream I3D as a backbone network. The two intermediate features at the end of the last max pooling layer are added in an element-wise fashion, and they are used as an input to the network for gaze modeling. The sampled gaze points are applied with both the fully connected layer and the sigmoid function to produce a soft attention map. We evaluate the proposed method on the two popular datasets, which are eGTA and GTA Gaze Plus. eGTA Gaze Plus is the largest dataset for egocentric activities and gaze that has over 10,000 video clips with 106 activity categories. These tables show the performance comparisons with state-of-the-art methods. The proposed method outperforms all the other approaches on both datasets. For qualitative analysis, we visualize the last convolutional layer's activations using GradCam++. From these figures, we can observe that the proposed method makes the network better at attending objects or regions that are related to the activities. Thank you for listening, and please feel free to visit our project page.